Coming to Bayes' law, this Bayes' law was actually applied to the previous law, that is the Lamberts concept, and this person simply he applied this concept to solutions of different concentrations and reported his results just prior to another person, as I said, was Bernard. So this person has done nothing other than he has taken his observation along with the thickness and the concentrations of different varying spaces. I would like to take you through the previous and the very discussion we had in this particular slide. So the Lamberts law was actually the intensity of the incident radiation with the thickness and the rate of decrease in the intensity with increase in the thickness. And the Bayes' law is basically the again with respect to the intensity of the incident or the rate of decrease in the intensity with respect to the thickness along with the concentration of this absorbing medium. He has added only one additional term, which is the concentration of these absorbing spaces. We call them as absorbing spaces. So basically he has applied or extrapolated the Lamberts law and he has made his law called as the Bayes' law. So we always call this as a Bayes-Lamberts law is because both the thickness and the concentration terms have been taken for any discussions we have hereafter. So coming to the definition, what the Bayes' law states. The Bayes' law states that it is when a beam of monochromatic radiation is passed through a solution of an absorbing substance, the rate of decrease of intensity of the radiation with the thickness of the absorbing solution is proportional to the intensity of the incident radiation as well as the concentration of the solution. So he has done nothing. He has taken one additional term, that is the concentration. So mathematically, the law can be expressed in the similar way as of that Lamberts law. So it is minus di by dx is equal to ki. Okay, and additional term, as I said, is the concentration term, which is included in this Bayes' law. So C is nothing but the concentration of the solutions, which is expressed in moles per dm cube or moles per liter. Okay, so K dash is the molar absorption coefficient. Okay, so previously it was the absorption coefficient. I'll take you back. It was absorption coefficient previously. I have written it in the next slide. Yeah, A is equal to the absorption coefficient, and now or the K is the absorption coefficient. But instead we have taken the concentration in moles per dm cube. It now becomes the molar absorption coefficient, and as I said, it is very specific for the medium, or it is very specific for the nature of the medium. So what we will do is we will again mathematically evaluate this particular statement what was made by Bayes. Suppose I naught be the intensity of the radiation before entering the absorbing solution when x is equal to A, and the intensity of the radiation I after passing through a thickness x, okay, of the medium, and it can be calculated as I naught. Incident radiation and transmitted radiation, as it tends from I naught to I, and as the thickness tends from 0 to x. Okay, so it is minus which will actually shift onto the right side of the equal to symbol. So it is as I naught tends to I, di by dx is equal to minus as x tends to 0, x tends to x from 0, it is k dash c dx. Okay, we have added one more term or the additional term compared to the Lamberts law, which is concentration term here. And finally, I am not going into very detail, I am just considering the Lamberts law and directly arriving at this equation, that is I is equal to I naught e to the power minus kcx. Okay, previously it was kx in Lamberts law, now it is kcx. Or the above equation can also be rewritten by changing the nature of logarithm to the base 10, that is I is equal to I naught 10 to the power ax in the Lamberts law. Now it is a dash cx. I want to change this from a to a dash is because the absorptivity since it is expressed in moles per dm cube, I am writing it as A dash minus ACx. C is the concentration term, x is nothing but the thickness. So here K dash by 2.303 is A dash, and A dash is nothing but again an absorption coefficient. Since we have expressed the concentration in moles per dm cube, now it becomes molar absorption coefficient of that particular absorbing solution. So basically, on combining both the Lamberts law and the Beer's law, we have the Lamberts law on to my left, that is I is equal to I naught 10 to the power minus Ax, and the Beer's equation is nothing but I is equal to I naught 10 to the power A dash Cx. A dash is different than A is because A dash is expressed in moles per dm cube, and C is the additional term what we have in the Beer's equation as compared to the Lambert's equation. So on combination of this Beer's and Lambert's equation, we have I is equal to I naught 10 to the power Acx. Okay, so there is an additional term C, and the absorption coefficient has been represented as small a. So on simplifying this equation, on applying log I naught by I is equal to Acx, or log I naught by I is equal to epsilon Cx, which is nothing but A. Okay, so A is nothing but the absorbance. Okay, so I log absorbance is nothing but it is the log of I naught by I, which is equal to epsilon Cx. What is epsilon? I have represented this epsilon because it is the molar absorptivity, or also known as molar absorption coefficient. C is nothing but the concentration of the solution, which is expressed in moles per liter, and x is nothing but the thickness or the path length of the sample, which is usually expressed in centimeters. Okay, so I hope now you understood. Log I naught by I is nothing but the absorption, which is equal to epsilon Cx. We can also call it as A is equal to epsilon Cx, or some people will also call this as A is equal to ABC. Okay, small a, small b, and small c. Small a is nothing but the absorptivity, b is nothing but the thickness, c is nothing but the concentration. Okay, some people express it in a very different way. So finally, we have A is equal to epsilon Cx, or A is equal to capital A is equal to small a, small b, and small c. So out of this understanding, we have several definitions which come into picture. So we have absorptivity and absorbance now. What is absorbance in the previous equation? Absorbance is this term, whereas the absorptivity is this particular term. Okay, so absorbance is different, absorptivity is different. For that reason, we have two terminologies here, absorptivity and absorbance. Absorbance is an extensive property of a substance, whereas absorptivity is an intensive property. Okay, intensive property, I mean to say the bulk property. Okay, absorptivity is the bulk property, and absorbance is an extensive property. Okay, if there is a change in the concentration and the thickness of the container, the value of molar absorptivity will remain constant, whereas the Beer's range, but the absorbance will change significantly. I will repeat it. If there is a change in the concentration and thickness of the container, the value of molar absorptivity will remain constant, whereas within the Beer's range, whereas the absorbance will change significantly. Okay, so I can correlate this term. The molar absorptivity will not change with concentration, whereas the absorbance will change with the concentration. So for that particular system, either if there is an varying concentration, but still within the Beer's range, if you are varying the concentration, the absorptivity remains same if you have taken that sample in one particular medium. Okay, so absorptivity, as I said, is an intensive property. Okay, whereas the absorbance which changes with the concentration, that is what this means. Okay, so the value of molar absorptivity will be different at different wavelengths. This is also very important thing which we should remember. So molar absorptivity will be same for different concentrations, but it will not be the same for different wavelengths. Okay, what different concentrations? The concentration, we have a range, something called as the Beer's range. Okay, so the Beer's range is nothing but once we prepare the samples in a varying concentrations, the absorbance what we get out of this concentration should be from 0.2 to 0.8. Okay, if the absorbance is between this particular absorbance value, that is 0.2 to 0.8, then the respective concentration what we have, we call it as the Beer's concentration. So when we prepare the solutions in the Beer's concentration, then the absorptivity will not change. Okay, whereas the absorbance will change. And when does the absorptivity will change? It will change when I change the wavelength. Okay, so these are the things which we should remember very carefully. Coming to even percentage 1 centimeter, this is a new term which you can expect for 2 marks or 1 mark question. The absorbance, we already know that log I naught by I is nothing but the absorbance. If the absorbance of 1% solution in a cell with a 1 centimeter path length, okay, I will repeat, absorbance of 1% solution in 1 centimeter path length, if we take the absorbance of that particular 1% solution in 1 centimeter path length, then whatever absorptivity value we get, we call it as E1% 1 centimeter. This is used in place of epsilon, which is absorptivity when the molecular weight of the compound is not known. Okay, so when I'm preparing a solution or moles per dm cube solution, I need to have a molecular weight. If the molecular weight of the compound is of unknown nature, then we don't have its molecular weight. In that particular case, we usually go for E1%. Okay, that is when the molecular weight of the compound is unknown, and whenever the compound is new of unknown molecular weight, then we usually go for E1% 1 centimeter, and then we will take account for its absorptivity. And epsilon, I just now mentioned, molar absorptivity, it is constant for an organic compound at a given wavelength and is reported as epsilon max. Okay, that is the molar absorptivity at an absorption maximum. Okay, these all things, this we will be doing in practical. This also will be employing, these two terms we will be employing in the practicals. Coming to the next term, that is transmittance. Transmittance is the ratio of I by I naught. Okay, it is simply the mere reversal of absorbance. Okay, or the reciprocal of the absorbance. Absorbance is the ratio of I naught by I or log 1 by T. It is what I have rewritten transmittance as. Okay, so these are some of the important terminologies which might be asked for either 2 marks or collectively for 5 marks. So after that we have some limitations of Lamberts law. This I will take up in the next session. So I hope you understood the terminologies. Absorption is different, absorbance is different, absorptivity is different, E1% 1 centimeter is different, and it is calculated whenever the molecular weight is unknown. And epsilon, or we also call it as E, the molar absorptivity is calculated for a molecule when the molecular weight is unknown. Okay, and the molar absorptivity remains fixed. It remains fixed even if you change the concentration, but still within the Beer's range, and the absorbance will change with the change in the concentration. So absorbance and absorptivity are two different terms which should not be confused one with the other. Transmittance is the reciprocal of absorbance, that is the ratio of I by I naught, and we already know that absorbance is log I naught by I, which can also be rewritten as log 1 by T. T is nothing but transmittance.